Hi everybody, this is lecture number 6 during the holidays of COVID-19. We ask the God to beat and overcome this COVID-19 epidemic. Say Amen, all of you. This lecture deals with the relationship between two variables. This relationship can be explained by what we call covariance. Covariance means التغاير, and correlation الارتباط, then regression الانحدار. So this lecture contains the covariance and the regression, and the next lecture discuss the regression. Okay, before explaining the covariance, I would like to say that chapter 5 cancelled, so you have to cancel chapter 5, which deal with the measurements of the shape of distribution. I mean the skewness and the kurtosis measures. Okay, so the covariance, the first measure, the covariance, the formula for computing the covariance of a population of size n, or a sample of size n, with observations of two variables x and y, are defined as the formula, and the covariance itself is computed and denoted by SXY for sample and sigma XY for population. Here, as we explained with the standard deviation in sample, we divided, or the denominator was n-1 for standard deviation. Okay, for a population the denominator was n. Okay, so as we did with the standard deviation, now the covariance is the summation of x minus x bar divided by y minus y bar. So x minus x bar means the deviations between the observation and its mean, and for the second variable, the deviation between every observation y and y bar, the mean of y. So we can say that we have to multiply the deviations of the first variable by the deviations of second variable, and divide by n-1. So you can say that the covariance is the average, okay, of the deviations, or of the summation of the deviations of the two variables, the average of the summation of deviations of two variables, right? Whether for a sample or for a population. Okay, so here the concept is the same, but we use sigma for population data and S for sample data. Okay, so SXY is the sample covariance, sigma XY is the population covariance, X bar is the sample mean of variable X, Y bar is the sample mean of variable Y, mu X is the population mean of variable X, and mu Y is the population mean of variable Y. Okay, according to the above formula, we must get the summation of the products obtained by multiplying the deviation of each X from its mean, X bar, or mu X, by the deviation of the corresponding Y from its mean also. This summation is then divided by n-1 for sample and divided by n for population. Okay, the positive value for SXY or sigma XY indicates a positive linear association between X and Y. Okay, so there is no limitations for the covariance. This covariance take any value between 0 and infinity. Okay, as the value of X increase, the value of Y increase. That's when the covariance is positive. Okay, when the covariance is negative, this indicates that there is a negative linear association between X and Y. So negative means in the range from 0 to minus infinity. So covariance may take any value between minus infinity to infinity. There is no limit. Okay, for covariance. However, we have a problem when using the covariance as a measure of the strength of the linear relationship. That's the value of the covariance depends on the units of measurement of X and Y. Okay, so the covariance may create a problem when the units of measures of variable X and variable Y are different. For example, assume that we are interested in measuring the relationship between heights and weights. Okay, you know that heights by centimeter, weights by grams or kilograms. For some students, clearly the strength of the relationship must be the same whether we measure heights in meter or centimeter. Okay, measuring the heights in centimeter, however, give larger value of covariance than measure heights in meters. Okay, so if you use centimeter instead of meter, the covariance will be larger. The covariance will be large. Okay. When in fact the relationship does not change. If you measure by meter or by centimeter, the relationship does not change. But according to the formula of covariance, you will see that covariance when measuring with centimeter is larger than covariance with measuring in meter. Okay, that's unlogic. A measure of the relationship between variables that's not affected by the units of measurement is the coefficient of correlation. Okay, so now why the coefficient of correlation is better than the covariance to express the relationship between two variables. Okay, what's the difference between coefficient of correlation and the covariance when expressing the relationship between two variables? Okay, so it's better to use coefficient of correlation instead of covariance. Okay, the function cov means covariance. The syntax, we have two syntax: C from covariance equal cov of A, or C equal cov of A and B. Okay, C equal cov of A returns the covariance. If A is a vector of observation, C is a scalar varied variance. Okay, so if the relationship between only one variable and itself is called the variance, because the variance is the average of the squared differences between observation and its mean. Okay, the average of the squared differences between observations and its means. Okay, so this is called variance, not covariance. Okay, so if A is a vector of observation, C will be a variance, not a covariance. Okay, not be a variance. So in this case, cov A equal var A. Okay, if A is a matrix whose columns represent random variables and whose rows represent observations, C is the covariance matrix with the corresponding column variances along the diagonal. Okay, so in the matrix of, it's called variance covariance matrix, okay, where the diagonal of the matrix represent the variances. Okay, the variances for all variables contained in the matrix. Okay, and the other entries in the matrix represent the covariance. Okay, So only the diagonal represent variances, and all the entries in the variance covariance matrix represent the covariance. C equal cof A and B returns the covariance between two random variables A and B. This is the case, okay? This is the case. Why? Because cof A represent a variance, not a covariance. So the covariance for one variable called the variance, okay? Example number 1. On 10 occasions during the past 4 months, a store used TV advertising to promote its sales. The following table shows the number of advertising, number of commercials, الإعلانات, and the value of sales in hundreds of pounds at the store during the following week. بنشوف المبيعات في الأسبوع التالي للإعلان. So this is a table. We have 10 weeks and the number of advertising or number of commercials in the second column, and the sales by hundreds in the third columns. Okay? Find the population and sample covariance and the measure for the strength of the linear relationship between the number of commercials, number of advertising, and the sales denoted by Y. By hand, you have to construct a table like this. The first column represents the variable X. The second column represents the variable Y. The third column, the deviation of X, denoted by X minus X bar, where X bar is the mean of X. Here, sigma X equal 30. So the mean is 30 divided 10, the number of weeks. So the mean equal 3. And for the second variable, the deviation represented by column 4, then the multiplication of deviations for X and Y represented by column 5. Okay, so X bar equal 30 divided 10 equal 3, and Y bar equal 500 divided 10 equal 50. Then the covariance for a sample equal 1 divided n minus 1 sigma X minus X bar divided Y minus Y bar. This equal 1 over 10 minus 1 multiplied by 94, this column. The last column summation is 94. So the covariance for the sample equal 10.4. For a population, the covariance will be 9.4. So the covariance of sample is larger than the covariance of population. Why? Because the denominator for sample is smaller than the denominator for a population. Okay? So you can say that the covariance for a population data is less than that for a sample, or the covariance for a sample is larger than the covariance of population. This is like the variance and the standard deviation. As we said before, the variance for population is less than the variance for sample, and also the standard deviation for population is less than the standard deviation for a sample. Okay, by MATLAB we can use the function COF. Okay, after entering the data for variable x and for variable y, Sxy equal COF x and y. This will give you the variance covariance matrix, where the main diagonal represent the variances. This is the variance for x, and this is the variance for y, and the other diagonal represent the covariance. Okay, the covariance between x and y looks like the covariance between y and x, but the variance of x is different from the variance of y. Okay, so this matrix called variance covariance matrix, right? Covariance for population denoted by sigma xy equal COF x and y and 1, x and y and 1, y1 for population at 1. Okay, so this is the covariance equal 9.4, and this is the variance of x and the variance of y for population data, okay. So as you see, the variance for population is less than the variance for a sample for variable x, and also for variable y. The variance of y for population is less than the variance of y for a sample. Coefficient of correlation or correlation coefficient. Another measure of the association or the relationship between two variables is the correlation coefficient. It's called Pearson coefficient of correlation, or Pearson product moment coefficient of correlation. I will go to the formula of coefficient of correlation, but before that I would like to say that the range of coefficient of correlation is between -1 and 1. Okay, so this is another difference between covariance and correlation, or covariance and coefficient of correlation. The covariance range is between -infinity to +infinity, but the range of coefficient of correlation is between -1 and +1. Okay, we have a lot of formula to calculate the coefficient of correlation. Rxy is the coefficient of correlation equal Sxy, the covariance between x and y, divided S of x multiplied by S of y. So you have to divide the covariance of the two variables by the standard deviation of every variable. Okay, here the denominator is the standard deviation of variable x multiplied by the standard deviation of variable y. The numerator is the covariance between x and y. Okay, another formula, r equal the square root of r square. R square here called coefficient of determination. Coefficient of determination. So coefficient of correlation is the square root of coefficient of determination. Or you can say that the coefficient of determination is the square of coefficient of correlation. Okay, here look, the numerator is the same as the numerator of the covariance. Okay, so here the same denominator, the same numerator for variance and for coefficient of correlation. The denominator is the square root of the squared differences for the two variables. Okay, so the denominator is the multiplication of the squared differences of the two variables, then take the square root of these squared differences, right? Okay, so here the multiplication of differences as covariance, and the denominator the square root of the squared multiplications of the deviations for the two variables. Okay, another formula. I prefer this one, really I prefer this one. R equal the square root of r square. The numerator here is n sigma xy minus sigma x sigma y divided the square root of n sigma x squared minus sigma x all square multiplied by the square root of n sigma y squared minus sigma y all square. Okay, here we don't multiply the differences. Okay, so we eliminate the fractions or decimal points when the deviation contains a fractions. Okay, here the computation of R contains the multiplication of x by y. Okay, then x squared and y squared. So we need x multiplied by y and x squared and y squared. Okay, 3 columns we need to compute the coefficient of correlation. And as we said, this coefficient of correlation must be between 1 and -1. Okay, as r near to 1, there is a positive relationship, and as r near to minus 1, there is a negative relationship, right? The function core, linear or rank correlation. So the function core measure the coefficient of correlation for person and also for Spearman rank correlation, Spearman, as we will see later. Okay, so here rho equal core of x or core of x and y, or you can use rho and b val equal core of x and y, or rho and b val equal core x and y and name and the value. Okay, we will use this one, and we have also another function called core coef, and I will explain the difference between function core and the function core coef. Okay, the first syntax is rho equal core of x returns a p by p matrix containing the pairwise linear correlation coefficient between each pair of columns in the n by p matrix. Okay, so the data must be entered or written as columns. It's an important point, as columns. So x is a column or x is a matrix. Okay, and also y is a column or a matrix. Okay, so the difference between core x or y and the function core coef is that core coef of x and y returns a matrix of correlation coefficient for the two column vectors x and y. If x and y are not column vectors, are not columns, like core depend on columns. The data must be arranged in columns, but with core coef you can put the data as columns or rows, because core coef will convert them to column vectors. Okay, so if you write the data as a rows, the core coef will change or will convert these rows to be columns. Okay, this is the difference between function core and core coef. Okay, and also the result of core is the coefficient of correlation, but the result of core coef is the matrix, as you will see later. Example 2. Compute the correlation coefficient for the sample and population data involved in example 1 by hand. And using the first formula, S of x, the standard deviation for variable x, equal the square root of variance, and the variance equal sigma x minus x bar squared divided n minus 1. So the square root of the variance equals the standard deviation of variable x. Okay, for population data, sigma x equal the same numerator, but the denominator will be larger than that of the sample, because the population, when calling the population, we divide by n. When dealing with sample, we divide by n minus 1. Okay, so the standard deviation of population is less than the standard deviation of a sample. For the second variable, the standard deviation for sample equal 1.5 extremely, and for the population is 1.4. Okay, also the standard deviation for population is less than the standard deviation for a sample. So the coefficient of correlation between x and y equal 0.92. Okay, so the coefficient is 92%. 92%. It's nearest to 1. So this is a positive relationship. Okay, for population data, also the coefficient of correlation is equal 29%. Okay, so the coefficient of correlation for a sample is the same as the population. Okay, but the standard deviation of the sample is larger than the standard deviation of population, but the coefficient of correlation is the same for a sample or for a population data, right? By MATLAB, the function core here use a data in shape of column, this data in shape of row, and this data also in shape of row. So you have to transfer any row to be a column. So this is X transpose. X transpose is a column, where X is a row, and also Y transpose. Okay, so to use the function core, the data must be ranked in columns, not in rows. Okay, so the coefficient of correlation is 92%, like this. Using the core coef, the result is a matrix, not an integer, the matrix. Okay, where this one means the correlation between x and x, okay, and this the correlation between y and y. So the correlation between any variable and itself equal 1. Here the perfect relationship with the variable and itself، ارتباط المتغير مع نفسه يساوي ارتباط تام، perfect correlation يساوي 1. لكن ارتباط x مع y يساوي 92% as you see, right? Example 3, another example. Here we use the third formula. This is x, this is y and x. Then we construct the third column denoted by x multiplied by y, then x squared, then y squared, right? Here the number of observation is 5 for every variable, and we will use r equal n sigma xy minus sigma x sigma y divided the square root of n sigma x squared minus sigma x all squared divided the square root of n sigma y squared minus sigma y all squared. This will be 73%. Okay, it's positive also. So the relationship is positive and near to 1. Okay, here x and y are equal core x transpose and y transpose equal 73%. Okay, the same. Now the coefficient of correlation when dealing with ordinal data where x or y is ordinal, you have to use Spearman rank correlation, not Pearson correlation. Okay, so Pearson correlation or coefficient of correlation deals with quantitative data. When one variable is ordinal, you have to use Spearman rank correlation. Okay, so the previous two parts of this chapter we have dealt only with quantitative variables. So covariance and coefficient of correlation deals with quantitative variables. In many situations, however, one or both variables may be represented by ordered or ranked data. In such cases, we cannot use the covariance or Pearson coefficient of correlation. Okay? To describe the relationship between the two variables. Okay? However, we have to use the Spearman rank correlation coefficient, which utilizes the ranks of the data rather than the original data themselves. Okay, so Spearman coefficient of correlation or rank correlation denoted by RS measure the relationship between ordinal data or quantitative data. Okay, so in this case we can use Spearman rank correlation to measure the relationship between two quantitative data or one ordinal and one quantitative or two ordinal data, two ordinal variables. Okay, rank, Spearman rank denoted by RS equal n sigma AB minus sigma A sigma B. Okay, look at the numerator here and compare with coefficient of correlation. Okay, for coefficient of correlation the numerator is n sigma xy minus sigma x sigma y. We replaced x by a and we replaced y by b. Okay, so this is the same formula for coefficient of correlation after substituting x by a and y by b. هي نفس الصيغة لكن بدل x و y هتحط a و b. طب a و b هي ايه؟ هنعرف دلوقتي. في صيغة تانية لمعامل ارتباط سبيرمان rs equal 1 minus 6 sigma d square divided n multiplied by n square minus 1. هو d square ده الفرق ما بين رتب a ورتب b، يعني رتب x ورتب y. لكن هنا a يعني رتب x و b يعني رتب y، يبقى هنا احنا بنتعامل مع الرتب مش مع البيانات. okay, when measuring Spearman coefficient of correlation we deal with the rank of data, not the original data, the rank of data, right? Don't forget that. Where a and b are the ranks of the variables data and d equal a minus b, the difference between the rank of x and the rank of y. Example number 4. The following table gives the price and the quality scale of a sample. Quality scale means ordinal data. Price means quantitative data. Of a sample of 5 brands of fans. 5 أنواع من المراوح. fan brand A B C D F دول 5 مراوح. quality scale الجودة 8 9 4 4 6. price 550 600 420 480 620. okay, find the Spearman rank correlation coefficient between the quality scales of the fan brands and the price by two methods. By two methods means use the two formulas. Solution by hand. 3 columns are given before. Then A is the rank of X, B is the rank of Y, D is the difference between A and B, D squared is the square of D. Okay, so for quality, look, the smallest values are 4 and 4. So the range here, or the rank, will be 1 and 2. Because they are equals, then get the summation of 1 and 2 equals 3 and divide by 2. So the rank of everyone equal 1.5. So this is 1.5 and that is 1.5. okay, next, quality 6 equal number 3 ranked as 3 and number 8 ranked as 4. Then the largest scale is 9 ranked as 5. okay, here for the other variable, the price, this is the smallest 1, so the rank equal 1. Next is 480, number 2. Next 550, number 3. 600 number 4, 620 number 5. A minus B equal D. So 4 minus 3 equal 1, 5 minus 4 equal 1, and so on. D square equal D, 1 by 1 equal 1, 1 by 1 equal 1, half by half equal a quarter, and so on. First method, RS equal 1 minus 6 sigma D square divided n multiplied by n square minus 1. 6 multiplied by 6.5, this one, D square, divided the number of observation, number of pairs, 5 multiplied by 5 square minus 1. So Spearman rank correlation equal 67%. 67%. Second method looks like the calculation of coefficient of correlation after substituting x and y by a and b, okay. So this is a, rank of x, this is b, rank of y, a square, b square, ab. Then apply the formula, this formula, then the coefficient of Spearman correlation equal 67%. By MATLAB, we use the function core, but we have to add type Spearman, okay. So the syntax core x and y and the value and the name and the value means put type and Spearman between quotation, type between quotation and Spearman between quotation, okay. This will give you the Spearman coefficient of correlation like this, okay. So we will stop here, and the regression analysis is the subject of the next lecture. See you next week. Thanks a lot.